Okay, so for Race to the Finish pulley, we've got a cart that's on a flat horizontal surface. It's on the table, and it's being pulled by a mass on a string. Okay, so let me draw that for you. We've got the pulley, we've got the table, we've got the cart, and we've got a string tied to the cart, and on the other side we've got a mass hanging. Okay? So what's happening here is gravity is pulling on the mass. So instead of the cart's mass, so mass of the cart doesn't really matter. It's the mass of this hanging mass, okay? And so these masses, it can be 10 grams, I think 20 grams, and then 50 grams. I think anything above that is too fast. Even 50 grams might be too much. Okay, and then gravity is 9.8 meters per second squared. All right, so we have this force, F of G, pulling down, and you can think of it this way. There's a mass here, and then here's the cart itself. All right, and I think we measured the cart. The mass of the cart is roughly 55 grams. Okay, and so there's going to be a force pulling on both of these things. And you're going to use Newton's second law, F equals ma, to determine acceleration. All right, but this m is not just here, it's the two masses together. Okay, so what does that mean? That means if I bring up this mass up to the top here, and I let go, it's not going to fall down at 9.8 meters per second squared. It's actually going to fall slower. Why is that? Is because it's carrying along, it's pulling along the cart itself. Okay, so we're going to draw and do some math here, but I just wanted to introduce the scenario to you. You've got cart, you've got a flat surface, you've got some string, you have a pulley, and you have some mass, some hooked mass. Okay, and I'm just drawing, it's almost like a free body diagram, but it's more like a linear diagram of what's going on. The pulley itself is just redirecting the force, so instead of an up and down force, it's a horizontal force. Okay, so the goal again is finding time using acceleration. And so where did we see acceleration? We see it right here in F equals ma, but force and mass is all kind of tangled up here in this situation. There's the hooked mass and there's the cart mass. All right, so let's just start with a 10-gram mass. All right, so let me write 55 grams here. All right, different carts might weigh a different amount depending on what model, because we have newer blue carts and we have some of the older blue carts. They might actually be slightly different in terms of weight and mass. But what's going on is we want to get this cart, the front of this cart, to maybe strike a wooden block some distance away. So we can adjust this distance a certain amount. Something that's different from the ramp problem is that we are actually limited by the height of the table. So if this is the floor, if this is the table leg, and here's the floor, there's carpet here, all right, we can only raise the mass up a certain amount h, and I think our limit was like 75 centimeters. Okay, I have the meter stick. Hold on. Okay, so using our science tables, it is exactly 75 centimeters. So let's just stick with 75 centimeters. We don't have to pull back all the way, but our limit, D, needs to be greater than or less than or equal to 0.5 meters. Okay? All right. So now we can do some math. I know that the force on this system is mg, the mass, so it's going to be 0.010 grams times 9.8 meters per second squared. So this is F of g, or net force. All right, M is going to be equal to the M1 plus M cart. All right, and that's going to be 0.010 grams plus 0.055 grams, and that equals 0.065 grams. Oh, sorry, kg, because I already moved it, right? So 10 grams, if I move it 1, 2, 3, right, that's 0.010 kg. Okay, so glad I caught that, or else my answer would have been off by 1,000. Okay, and acceleration is what? Well, using F equals ma, then A equals F over m. That is 9.8 times 0.01 divided by 0.065. Okay, put it into my calculator. 9.8 times 0.01 divided by 0.065, and I get an acceleration of 1.51 meters per second squared. Okay, and then what I'll do is we'll use distance equals 1/2 at squared, and for my distance I know that it needs to be less than 0.75 meters, so I'll just plug in 0.7. Actually, we'll solve for t first. All right, so ignore that. T equals 2d over a square root. A, though, we can change a to anything. Sorry, not anything. We can change acceleration and increase it by changing the masses. Right, so we'll call this A1, and we'll call this A10, A20, and A50. All right, so if we want less time, of course, we can divide by a larger number. All right, so if I were to just plug in everything, it would be 2 times 0.7 divided by 1.51, square root the whole thing. And it would be 2 times 0.7 divided by 1.51, and then square root. And I would actually get 0.96 seconds, which is, actually, that seems kind of low to me. Don't you think? I feel like within 1 second, it should actually take longer. But this is just the numbers that I'm using to calculate. All right, F equals ma, d equals 1/2 at squared. Yeah, so in order to cover 0.7 meters, well, that's the numbers that I'm getting. Now you can work it out if we used 20 grams instead. So A equals F over M total, right? F would actually be 0.02 times 9.8, and M would be 0.02 plus 0.055. Okay, so that would be 9. What's the bottom here? 0.02 plus 0.055, 0.075. Okay, so 0.02 times 9.8 equals, divided by 0.075, so acceleration then would be 2.61. And if I divide 2 times 0.7 divide by 2.61 and square root this, I would get A would equal 0.73 seconds. Oh, wait, not A. So T T for 20 grams would be less. So at least we have that. Okay, so using these numbers, of course, this is all just calculations. In a perfect world, that means there's no friction. That means everything is moving along the way we want it to. But because of friction, that might slow things down. The string also, if we have an ideal string, that means the string is massless as well, which is not true. Everything has mass. Everything made of atoms has mass. But we aren't expecting a perfect answer. All right, you might be off by a little bit, and the goal is to practice using the kinematic equations to set the time of the pulley, T pulley, equal to time of the ramp. So how long does it take the two cars to reach the finish line? We want them to reach the finish line at the same time. Okay, so pull the pulley back, right? So the car is being pulled by the string, and then put the second car up the ramp at a certain distance. When you let go, they should both hit the finish line at the same time. All right, so let's just review real quick before I end, and then you can work on your calculations. What you need to do is determine the mass and determine the distance. Okay, so you have to choose 10 gram, 20 gram, or 50 gram, and then you have to choose a distance such that the time that it takes the pulley car to reach the finish is equal to the time it takes the ramp car to reach the finish. All right. So pulley cart, you start with force of gravity. It is the mass, this mass being pulled down at 9.8 meters per second squared. Okay, that's the force on this entire system. But that's not the force that accelerates. Its force of tension is not the same as force of gravity. All right, so the tension is accelerating the cart, but not as much as mg. All right, the total mass is this, and we use F equals ma, or A equals F over m, to find acceleration. So this is A10. Acceleration of the system, acceleration of the cart with 10 grams of mass hooked onto the string. And I did it for 20 grams also. After you find acceleration, you can plug it in here. Distance we said was 0.7 meters, and solve for t. T equals 2d over a square root. And then we got 0.96 seconds. If we added more mass, if we doubled the mass, that means we would double the force, and we would get 0.73 seconds. All right, so let's just summarize. You're going to have a ramp and a cart, and you need to determine angle and distance. We'll call it dr, and this is angle. And you're going to have a pulley with a string, and you're going to have a mass, and you're going to have a distance. We'll call it dp, pulley. All right, so you need to find these numbers. Determine this, right? Angle of incline. This is distance up the ramp. Distance pulled back. Okay, and remember this is less than or equal to 0.75 meters. And then mass, you have roughly 3 choices. Yeah. So these are the masses that we have here in the lab. So you need to find these 4. So, and your goal is to have T pulley to be equal to the T ramp. Okay. All right, and that's the challenge. You do your calculations, you set up everything, the ramp and the pulley system on the same table, and then you call me over and you release at the same time, and we see if your calculations were correct. All right, so that's race to the finish, ramp versus pulley.